Up until now, we've only been talking about particle motion. That's motion where we assume the object has no length dimensions, and so we can't talk about orientations at all. We can't think about whether the thing is spinning or rotating. We can only think about how the location of the object is changing. Now we're going to start talking about rigid body motion. So I'm sort of going to use these three things interchangeably. So rigid body is kind of going to be the same thing as angular and the same thing as rotational. So when you see these things, what we're talking about is the distinction between a particle and a body that we are treating as having length, and we are taking into account the changes in its orientation. What I mean by that will be clear once I start drawing pictures. And we're going to start with kinematics. Kinematics means we're not taking into account forces and masses and stuff like that yet. So for now, we're just going to be describing the motion, defining some new quantities. In this stuff, we are always going to be thinking about an object. So here's just some random object, okay? And it's always going to be free to rotate around some point, okay? And that point I'll refer to as a hinge or a pin or a fixed point, okay? So that location doesn't move, but every other point of this body moves in a circle around that pin as the object moves. Okay, so you can imagine if we're thinking about what does this point do as this object changes orientation, it moves around in a circle like that. And that's true of every point on this body. The size of the circle just changes. So the first definition that we're going to need is angular position. And I'm going to use theta to represent the angular position. And to define a body's angular position, you have to choose a reference orientation of the body. And then at a given instant, the body's orientation, if you measure the angle from this reference location to its current, from the reference orientation to its current orientation counterclockwise, that's positive. So a counterclockwise angle from the reference is positive. And a clockwise angle from the reference orientation is negative. That's probably backwards from what you would expect, but that's just how it is, and it all relates to vector math and stuff that we're not going to go into, but you just have to kind of accept this as the new sign convention. So counterclockwise is always positive, and that's going to be always true in all of these rigid body angular calculations. The units that we're going to use for angular position, this is important. This has to be in radians, not in degrees. You probably aren't going to have to change your calculator to radians to do these calculations ever, if I'm thinking right. Definitely not very often. The only reason you ever need to change from radians to degrees and back is if you're using trigonometric functions. So even though we're measuring these in radians, we're usually not going to have to use trigonometric functions with it. Okay, so let's think of a little example. So let's say that our reference orientation, we can think of it as like our zero orientation. Say this is a body, okay? I put that little line there to make it easier to tell so you can see what direction this object is oriented. So let's say this is our reference orientation. And let's think of two orientations and think of the angular position of the body in these two. Okay, so how would the body, if this is on the left, if this is what we're calling zero orientation, what would be the orientation of the one in the middle here? Well, you would have to rotate from the reference orientation 90 degrees or pi over 2 radians counterclockwise to get to this one. And so in this case, theta is equal to, counterclockwise is positive, so this is positive pi over 2. You could actually go the other way, you could rotate clockwise and you'd have to go 3 pi over 2 to get to this. So that's also a perfectly valid way to write this, is negative 3 pi over 2. Okay. This reference orientation, this is like our 0, so that's an angle equal to 0. So what about this one on the right? If we're going counterclockwise, positive, then this theta is 3 pi, positive 3 pi over 2. If we're going clockwise, we'd only have to rotate 90 degrees, so that's pi over 2. So that's the way that the angular position works. Next, we have to define the angular velocity. That's the Greek letter omega. And this is a quantity that tells you how quickly the angular position is changing. So this angular position theta is changing. And the derivative relationship, this can be, you can think of angular velocity as being defined by this derivative relationship that says omega as a function of time is equal to the derivative with respect to time of theta. So if the object is moving in the positive direction, if it's moving counterclockwise, omega is positive, and if it's moving clockwise, omega is negative. And so you can always think of omega as the sign of omega telling you what direction the object is rotating at any given instant. The SI units for angular velocity are radians per second. The last definition I'm going to give you right now is angular acceleration. And we're going to denote that with the Greek letter alpha. Looks like a goldfish. And this tells you how quickly the angular velocity is changing. We're going to give a derivative relationship to define the angular acceleration. And that is that Alpha as a function of time is the derivative with respect to time of omega. Okay, both of these derivative relationships are in that list of those 5 important ones that I've been giving through this whole class. One thing that you need to keep in mind about angular acceleration and angular velocity is this is analogous to the way it works with translational velocities and accelerations. So if omega and alpha have the same sign, think for a second, what do you expect? Would the rotations be speeding up or slowing down? It works the same way as translational quantities, so this means that the rotations would be speeding up. And on the other hand, if omega and alpha have opposite signs, the rotations are slowing down. Okay, so let's do a little calculation for this example problem. Let's think that we have the angular position as a function of time, and let's say that it's equal to 5t squared minus 3t plus 4. And we want to know 3 things. First, we want to know the angular velocity as a function of time. Second, we want to know the angular acceleration as a function of time. And then third, we want to know at a specific time, so at time 0.5 seconds, is this object, first, I guess, what direction of rotation do we have? And is it speeding up or slowing down? Okay, so for parts A and B, we're just going to use the derivative relationships. So omega as a function of time is the time derivative of this expression for theta. So this is equal to 10t minus 3. Now to get alpha as a function of time, we take the time derivative of omega. And so alpha as a function of time is just a constant value of 10. Then for C, to figure out what direction it's rotating, this is also analogous to the way it works with translational velocities. You just have to figure out the sign of the angular velocity in this case. Translational, it would be, you have to figure out the sign of the translational velocity. Okay, so omega at time equals 0.5 seconds is equal to 10 times 0.5 minus 3. And so that is 5 minus 3, so 2 radians per second. Okay. Well, that's positive, so it's rotating counterclockwise. And now to figure out whether it's speeding up or slowing down, we need to know alpha at time 0.5 seconds. This is a constant, it's just 10. I didn't give you this, but it's important. SI units for angular acceleration are radians per second squared. Okay, just pretend I did that before. Okay, so angular acceleration at 0.5 seconds is 10 radians per second squared. That's positive. So we know that the angular acceleration is counterclockwise. And so now omega and alpha at 0.5 seconds are both positive. And so that means that the rotations are speeding up. Okay, one more example with these. This time I'm going to start by giving you an angular acceleration function. So let's say that the angular acceleration at all times is equal to negative 12 radians per second squared. And so if we know that omega is equal to 4 radians per second at time 0, then first we want to calculate omega as a function of time. And second, we want to know, is this speeding up, well, let's say, what direction is it rotating at time 5 seconds? And is it speeding up or slowing down? At that instant. Okay. Well, we're going to use the derivative relationship, but the derivative relationship says that alpha is the derivative of omega, which means we're going to have to use the integral for this. So omega is the integral of alpha, and our alpha is negative 12 with respect to time. And so that is negative 12t plus a constant of integration. And now we have to use the initial condition to figure out what that c is. We're given that at time 0, omega is equal to 4. So 4 is equal to negative 12 times 0 plus c. And so c is equal to 4. And so omega as a function of time is equal to negative 12t plus 4. Now next we want to see specifically what's happening at 5 seconds. So for omega at 5 seconds, we have negative 12 times 5 plus 4. Negative 12 times 5 is negative 60 plus 4, so we have negative 56 radians per second. And you can see from the negative that it's moving in the clockwise direction. And now we have to figure out the sign of alpha at that instant. We're given in the problem that at every instant, where is it? Alpha is equal to negative 12. And so alpha and omega are both negative. And so this object's rotations are speeding up.